I've long thought about this idea since around 1996 in my college algebra course. In fact, I used to argue with my um, professor that there's more to a point than being zero dimension. Um, well, anyway, I'm sure you've heard of fractals, um, and you've heard of a fractal dimension between 2 dimensions and 3 dimensions. Well, what I want to discuss today is these things that I call fractal points and fractal lines. A fractal point, in a fractal point, I consider a region that is um, no signs of anything inside. And fractal lines are the things that intersect a fractal point. And I'll get to what a fractal line is. So here I go. And this is fractal points and fractal lines. And like I said, you start off with assuming a region that is hidden, a fractal point. And the only thing that comes out of it in any direction is a fractal line, an intersection of the point, the fractal point. So how the goal is with these things, the goal is to determine what polygon shape is in these hidden fractal points with only the knowledge of the fractal lines that come out of it. So, triangle, that's the simplest 2-dimensional polygon, but you don't know this is a triangle that's inscribed in this fractal point. But all you see is one line repeated going around. So you label one on both sides. That gives you 6. And what I've determined is that with constant numbers, like 1, 1, 1, 1, 1, 1, you do division. With alternating numbers, you do subtraction. 1, 2, 1, 2, 1, 2. So, what a fractal line is, it's a line that's broken up into a spectrum or a spectral line that can fit through a fractal point. And so, let me apply this math to this thing. You have 6 ones, so you divide. It's a constant number, so you divide 6 by 1. 1 being these numbers. And you get 6. Then you further divide. This is the second part that I didn't say, but you divide by 2 because there's 2 ends to these lines. So that gives you 3. There's 3 sides to a triangle. And the important thing to know is that it's open. It's an opening in this web, and this is a very simple web. Now I'll move on to a square. And there's repeating or alternating numbers, which is subtraction. 1, 2, 1, 2. There's one line going this way, and you label it both sides 1. 2 lines going this way. That's a fractal line. It's a double line. And this is a single fractal line. This is a double fractal line. These inscribe a square, but you don't know it's a square because this part is hidden. This fractal region, fractal point is hidden. Anything that's inscribed inside. So what do you do with the fractal lines? You count them 1, 2, 1, 2, 1, 2, 1, 2. So you know that it's alternating numbers. So you add up there's 4 2s. You add them up, that makes 8. 4 1s, you add them up, that makes 4. And you subtract, and you get 4. So there's 4 lines that make up a square in this polygon, this hidden polygon. And if you look at the rest of these, they do the same thing, and they They alternate between constant numbers, repeating numbers, constant numbers, repeating numbers, or alternating numbers, I'm sorry. Constant numbers, alternating numbers, constant numbers, alternating numbers. And you can see for yourself that this math does work. There's 10 twos. You label 2 on both sides of a pair of 2 fractal lines. And there's 10 of them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And so 20 divided by 2. 20 is the addition of all these 2's. Divided by 2 gives you 10. And you further divide by 2 because you're counting 2 twice. That gives you 5. So you know that's a pentagon. And it goes on like that. There's 6 3's. 1, 2, 3, 4, 5, 6. And there's 6 2's. 1, 2, 3, 4, 5, 6. And 6 3's adds up to 18. 6 2's adds up to 12. And you subtract and you get 6. And there's a 6-sided hexagon. Then you move on to a 7-sided. And it's constant numbers. So you add those up. And you get 42. You divide by 3, you get 14. You further divide by 2, it gives you 7. So it tells you there's a 7-sided, I don't know what the name of that is, polygon. It's out there. Do the same with this. And as you notice, this opening, closed, open, closed, this, and within this web, it gets tinier and tinier. The most largest is open triangle, and it gets smaller to the inscribed pentagon or negative pentagon, whatever. Then it's closed, and it's open, closed, open, and you can predict how these go. You got 6 1's, and if you just ignore the numbers here, you got 4 and 4, so that's 8. Then you got 10 2's, you ignore the 2, that's 10. 6, 8, 10. Ignore the 3 and the 2, and you get 6 and 6, that's 12. 14. Ignore the 3. 8 and 8 is 16. Ignore the 4 and the 3. And then, so, or 16. 8 and 8 is 16. So next comes 18. So it's 18 4s that go around here. And so I thought that this might be useful in the future to some sort of application. And the alternating opening and closed webs grow smaller as a polygon approximates a circle. And as a polygon approximates a circle, a fractal point becomes more point-like until an infinite-sided polygon would inscribe a point where the opening is just as much as a point as being closed. Well, I hope that this might be useful to somebody in the future. Thanks a lot.